In this A3 tutorial, we're going to look at why filters actually filter. Now, most students are quite well aware that this here is a low-pass filter and that this is a high-pass filter. And most students know that the cutoff frequency, and they can do all that sort of stuff. The question is, why do filters actually filter? And this is a question that some people simply cannot answer. So I'm going to provide you a simple explanation of why a filter actually filters. Now, a low-pass filter passes low frequencies and it filters out high frequencies. And the high-pass filter does the exact opposite. So and the standard sort of thing, as I said, that most students are quite well aware of is that for the low-pass filter you get this sort of response here where that roll-off is at 20 dB a decade. We have our cutoff frequency here, and at this point here the nominal cutoff frequency is 3 dB down. And this filter here, the high-pass filter, has the exact opposite response. Again, this is the nominal cutoff frequency and the minus 3 dB point. And again, that slope there is 20 dB a decade for one pole. And this is what we've got here. We've got a one-pole filter. Both of these are one-pole filter because they have only one, what they usually call active component. In this case, a capacitor. So this is what most students know. They can calculate the cutoff frequency. It's all fairly straightforward. The question is, why? Why do filters filter? And the answer is very simple. The reason is simply because of this graph, this relationship here, where we have frequency, we have impedance, and we know that for a resistance, the impedance is independent of it. A 5 ohm resistor is 5 ohms, irrespective of whether it's got 300 hertz or 3000 hertz through it. However, this is not the case with capacitors and inductors. We know that there's a linear relationship between frequency and impedance. XL is 2 pi FL. And we know the relationship between impedance and capacitance. XC is 1 over 2 pi FC. Now, in this particular diagram, this intersection here is purely coincidental, okay? And I'll even mark that. That's just the way I drew it. Coincidence. Okay, don't take too much the fact that they all bind over there. Now, let's think about what this filter here. Let's apply. We'll say that, for example, for 1 microfarad, and we'll pick a couple of frequencies. We'll say 1 microfarad at 100 hertz would have an impedance of round about 1,590 ohms. Okay. 2 times pi times 100 times 1 microfarad, 1 over all of that. The answer is about 1590. That exact same capacitor at, say for example, 50 kilohertz has a completely different impedance. The impedance there is round about 3 ohms. Now, think about that for a minute. A capacitor at a different frequency has a different impedance. We come back to our diagrams here, and we can see that if we look at the low-pass filter, we can see that for high frequencies, 50 kilohertz in this particular example, if this is a 1 microfarad capacitor, at 50 kilohertz, the impedance of this capacitor is a mere 3 ohms. So the high frequencies are shunted to ground. They see a very low impedance source. 3 ohms is effectively, it's almost a short circuit, okay? So all the high frequencies come in through here, then rather than get driven into whatever load is out here, for them it's much easier to drop down through here. So the high frequencies get shunted out, they get filtered out. The low frequencies at 100 hertz, they see this as being a much higher impedance. So the low frequencies, rather than go down through this this high impedance path down through here, the low frequencies will go this way. And that is why a low pass filter passes the low frequencies, because this is a much higher impedance down here, and the high frequencies get filtered out. If we wanted to, we could stick, say, if we were to say that this was going into a 600 ohm load, it's much preferable for a signal at 50 kilohertz, given the choice, is going to go through a 3 ohm load rather than a 600 ohm load. Similarly with the low frequencies, it's going to rather go to 600 than go into 1590. Similarly with the high pass filter, the same thing applies. For the very low frequencies, this impedance here is 1590. So the low frequencies get blocked. The high frequencies say, for example, at 50 kilohertz, that is merely 3 ohms. So the high frequencies go straight through here. That, in short, is why filters actually filter. It's all a matter of this relationship here, that at a low frequency, the impedance of the capacitor is very high, and at a high frequency, the impedance is much lower. That is why filters filter. Thank you for watching.